There is a boundary in space where physics itself stops making sense. This is the event horizon, the ultimate point of no return. It is not merely the edge of a black hole, but a frontier where our deepest understanding of space, time, and gravity completely shatters. By the end of this journey, you will grasp why this invisible surface represents one of the most profound failures in our description of reality. We will dissect what happens when an astronaut crosses this line, and explore the terrifying possibility that the universe forgets what falls in. How comfortable are you with the idea that some places in the cosmos might simply be unknowable? This surface is a line drawn by mathematics, not built from matter. An event horizon is not a wall of fire or a solid shell you could crash into. It is a boundary defined purely by gravity's relentless pull. At this specific distance from the black hole's center, the escape velocity, the speed you would need to achieve to break free and fly away, becomes exactly equal to the speed of light. Think of it like being caught in a river where the current gradually grows stronger. For a long time, you can swim against it, fighting your way back upstream. But there comes a point where the river's flow matches your maximum swimming speed. At that precise line, no matter how hard you paddle, you make no progress. You are stationary relative to the shore, suspended in a futile effort. Cross that line, and the current exceeds your ability to swim. You are carried inexorably downstream. The event horizon is that line for the fabric of the universe itself, where the gravitational current exceeds the cosmic speed limit. Nothing that crosses it, not a particle of light, not a radio signal, not a shred of information, can ever swim back upstream to the outside universe. It becomes a perfect one-way membrane. This simple, clean definition from general relativity, however, immediately warps our common sense. It creates a region of space from which the future itself has been cut off from the rest of the cosmos. And if nothing can come out, what does that do to the very nature of reality inside? The answer begins with spacetime not just bending but breaking. To understand this breaking point, we first need to grasp what is being broken. The stage for this cosmic drama is not empty space, but something far more profound. The universe is woven from a single, dynamic entity called spacetime. Think of it not as a static backdrop, but as a living, breathing fabric that connects all of existence. This fabric has 4 dimensions, the 3 of space we move through, and the 1 of time we experience. Now, this fabric is not rigid. It bends and stretches. What causes it to curve? Mass and energy. Every star, every planet, every single atom creates a tiny depression in this cosmic fabric. The more massive an object, the deeper and more severe the curve it creates. This is the core insight of Einstein's theory of general relativity. Gravity, the force that holds us to the Earth and guides the planets, is not some mysterious pull across distance. Instead, it is simply the experience of moving along the contours of this curved spacetime. Imagine you are a tiny ant walking on the surface of a trampoline. If the trampoline is flat, you can walk in any straight line you choose. But if you place a heavy bowling ball in the center, the fabric stretches into a deep well. Now, if you try to walk a straight line near that well, your path will naturally curve inward, pulled by the shape of the surface itself. You are not being actively grabbed by the bowling ball. You are simply following the geometry of the curved landscape. That is gravity. Planets orbit stars not because a force yanks them in circles, but because they are rolling along the curved grooves that the star's mass has pressed into spacetime. This common analogy of a ball on a rubber sheet is helpful, but it has one critical flaw. The sheet only shows a 2-dimensional surface curving into a 3rd dimension we can see. Spacetime curvature is not like that. It is an intrinsic curvature happening within all 4 of its own dimensions. There is no higher, 5th dimension for it to bend into. The fabric of reality itself is warping, and we are inside it. With this foundation, we can see a black hole for what it truly is. It is not just an object in spacetime. It is a place where the curvature of spacetime becomes so extreme so infinitely steep that the fabric forms a bottomless pit. The event horizon is the lip of that pit, the point where the slope becomes so vertical that nothing can climb back out. It is where the geometry of the universe becomes a one-way street to a destination physics cannot describe. This profound curvature is described by the language of mathematics, a set of equations that map the warps and wefts of spacetime. Just months after Einstein published his theory of general relativity in 1915, a German physicist named Karl Schwarzschild found a solution. Stationed on the brutal front lines of the First World War, amidst the hardship and conflict of the trenches, Schwarzschild performed a staggering intellectual feat. He solved Einstein's immensely complex field equations for the simplest possible case: a perfectly spherical, non-rotating mass sitting alone in an otherwise empty universe. The result was a precise mathematical description, now called the Schwarzschild metric. This metric is not a list of parts. It is a formula that tells you how spacetime itself is shaped around the object. It defines the rules for distance and time at every point surrounding the mass. And hidden within this elegant solution was something astonishing: a mathematical ghost. The equations contained a specific, critical distance from the center of the mass, a radius that depended solely on how heavy the object was. This is the Schwarzschild radius. For any mass, you can calculate it. For our Sun, it is about 3 kilometers. For Earth, it is a mere 9 millimeters. At this specific radius, the mathematics of the Schwarzschild metric does something bizarre. It appears to break. Terms in the equation blow up to infinity, suggesting that gravity becomes infinitely strong and time grinds to a complete halt. This mathematical singularity initially horrified physicists, including Einstein, who believed it must be an artifact, a flaw in the description, not a real feature of nature. And they were partially right. This breakdown at the Schwarzschild radius is not a true physical singularity where the universe ends. Instead, it is a coordinate singularity. Think of it like using a flat map to navigate the globe. At the North Pole, the concept of longitude loses all meaning. Every direction is south. The coordinates on your map fail, but the ground beneath your feet is still solid Earth. The pole itself is not a tier in the planet. It is just a place where our chosen system of labels becomes useless. The Schwarzschild radius is like that pole for spacetime. It is a location where the specific mathematical coordinates used by Schwarzschild, a distant observer's ruler and clock, cease to be meaningful. They cannot describe crossing that line. But this coordinate failure is not a mistake. It is a signal. It is the universe's way of marking, in the pure language of geometry, the exact location of the event horizon. The radius defines the horizon size with chilling simplicity. The more mass you compress within that radius, the larger the horizon becomes. This mathematical ghost was the first clear prophecy of where space breaks down, a warning written in equations long before we had any concept of a black hole. But if the horizon is just a coordinate illusion, what would crossing it actually feel like? The mathematical prophecy of the horizon gives us a map, but it tells us nothing about the journey. To witness an object's final approach is to watch physics perform a magic trick in slow motion. From the safety of a distant observation post, you train your telescope on an astronaut, brave or perhaps foolhardy, who has chosen to descend toward the black hole. As they begin their fall, everything appears normal. They are moving, communicating, their ship's engines glowing against the dark. But as they draw closer to the event horizon, a strange and inexorable process begins. The first sign is the light. The photons struggling to escape the immense gravitational well are sapped of their energy. Their wavelengths stretch out, shifting from the blue end of the spectrum toward the red. As the astronaut nears the point of no return, this red shift becomes extreme. The brilliant white of their hull dims to a deep crimson, then to a faint infrared glow invisible to your eyes. Their final transmissions, whether a voice signal or a data stream, drop in pitch and slow to a drawn-out, deepening drone before fading into radio silence. But the strangest effect is not on the light's color, but on its timing. You are watching events unfold in a region where time itself is bent to its limit. The gravitational time dilation predicted by Einstein becomes overwhelmingly powerful here. For every second that ticks on your clock, far from the black hole's influence, only a fraction of a second passes for the astronaut falling in. From your perspective, their clock is running slower and slower. Consequently, all their actions appear to decelerate. Their movement toward the horizon seems to grind down from a steady descent to a gradual creep, then to an imperceptible crawl. They are not stopping, but from your vantage point, the rate at which they approach that final boundary approaches zero. They become a fading statue, etched onto the surface of the horizon itself. You would watch for years, centuries, millennia, and never see their silhouette actually intersect that mathematical line. The universe, from your external point of view, has placed the astronaut in a state of eternal, asymptotic approach. The event horizon acts as an infinite time cliff. It is a surface where, to the outside world, time effectively stops. This is not an illusion of light or perception. It is a direct consequence of spacetime's extreme curvature. The future of the falling object, from your perspective, has been stretched out across the entirety of cosmic time. They are forever falling, forever almost there, but never quite arriving. This leads to a profound and unsettling paradox. From the outside, information about the astronaut, the pattern of atoms that made them, is never lost. It is smeared and frozen across the horizon's surface, a holographic fossil of their final moment. But from the inside, from the astronaut's own perspective, the story is utterly different. Their clock ticks normally. They feel no barrier, no dramatic moment of crossing. They pass through the horizon in a finite and perhaps brief amount of their own time, heading toward whatever awaits at the center. So which reality is true? Is the astronaut eternally preserved on the horizon, or have they plunged through it to a different fate? The universe, according to our best theories, cannot allow both stories to be true simultaneously. This is the beginning of the black hole information paradox, a crack in the foundation of physics that starts right here, at this illusion of an infinite cliff. From your distant vantage point, the astronaut is a frozen monument, but step into their shoes and the entire story rewrites itself. For the person falling toward the black hole, the laws of physics in their immediate vicinity hold firm. Their instruments register no alarms. Their body feels no sudden pull or tearing sensation as they cross the mathematical boundary of the event horizon. According to their own wristwatch, there is a precise moment when they pass from the universe where escape is possible into the universe where it is not. It is a moment as quiet and unremarkable as crossing the county line on a long road trip, marked by no signpost, no change in the road. The radical disconnect is not in what they feel, but in what they see when they look back. As they fall inward, the gravitational lensing becomes a cosmic projector. The entire history of the universe outside the black hole appears to speed up before their eyes. Light from events that took billions of years to unfold streams toward them, compressed into their final moments. They would witness stars aging and dying in flashes, galaxies evolving in a frenetic blur, a hyperlapse of cosmic history playing out in the shrinking circle of sky above them. Yet this spectacular show is the view from a train speeding down a tunnel as the entrance rapidly shrinks to a point of light, and then winks out. They are not watching the future. They are catching up on all the light that has been chasing them, light that was delayed by the intense curvature of spacetime. Once that last photon from the external universe enters their eyes, the tunnel entrance seals shut. No new information can reach them. The outside cosmos, in any meaningful causal sense, ceases to exist for them. Their future now lies irrevocably in one direction, toward the center. This is the first major crack in a unified description of reality. Two observers, both using the same laws of physics, describe two utterly incompatible truths. One sees a person preserved forever in time, their information smeared across a surface. The other experiences a smooth, finite journey into the unknown. General relativity insists both perspectives are equally valid, that there is no preferred frame of reference, yet they cannot both be physically true. This paradox is not a puzzle to be solved with better math. It is a fundamental warning that our understanding of spacetime is incomplete. The smooth geometry of Einstein's universe allows this schism to happen, suggesting that at the horizon, the very concept of a single objective reality begins to fray. This schism in reality points to a deeper fracture in the fabric of the cosmos itself. The event horizon does not just create two different stories, it destroys a concept we take for granted, the ideal of now. In our daily lives, we operate under the assumption of simultaneity. If two events happen at the same time for you, they happen at the same time for everyone, right? This intuitive notion is the bedrock of a shared, objective reality. But Einstein's relativity already taught us that simultaneity is relative. Observers moving at different speeds can disagree on whether two distant events occurred at the same instant. Near a black hole, this effect is not just a subtle shift. It is catastrophically amplified by the extreme warping of time. Consider the precise moment our falling astronaut's hand passes through the event horizon. For them, with their watch ticking normally, there is a definite now when that event occurs. But for you, the distant observer watching their eternal, frozen approach, the now of that crossing is stretched across infinite time. It is an event that, from your perspective, never actually happens. These are not just two people seeing the same event differently. They are two valid observers recording fundamentally different, irreconcilable sequences of events in the universe. The astronaut's now of crossing and your now of observing are completely disconnected. This means there is no universal clock, no master schedule that can synchronize what happens inside the horizon with what happens outside. The coordinate system of spacetime itself, the very grid we use to map cause and effect, becomes tangled and meaningless at this boundary. It is as if two people are trying to use the same map, but one person's north is the other person's yesterday. The directions no longer align. This breakdown of simultaneity is more than a philosophical curiosity. It is a direct signal that the smooth, continuous geometry described by general relativity is reaching its breaking point. The equations allow for this coordinate chaos, but they cannot resolve what it means for information, for causality, for the simple question of whether an object is inside or outside the horizon at a given time. The universe seems to be telling us that our comfortable ideas about a single, flowing present are illusions that dissolve under extreme gravity. If we cannot agree on what is happening now, can we even say that the inside of the black hole and the outside exist in the same universe at all? This question forces us to confront the true nature of the vacuum, the empty space that the horizon cuts through. The smooth, silent crossing of the horizon offers only a temporary reprieve. While the geometry of spacetime may allow a quiet passage, the physics of gravity soon asserts itself with terrifying, literal force. This force is not a uniform pull, but a difference, a gradient. Think of the tide on Earth. The moon's gravity pulls on our planet, but it pulls slightly harder on the side of Earth facing the moon than on the far side. This difference stretches the oceans, creating the high tides we see. This is a tidal force, the variation in gravity across a distance. Near a black hole, this gentle tidal stretch becomes a cosmic rack. As you fall feet first toward the center, the gravity at your feet is measurably stronger than the gravity at your head. Your body is not just pulled downward, it is pulled apart lengthwise, stretched. At the same time, the sides of your body, all being pulled toward the same central point, are compressed inward from all directions. This combination of radical stretching and simultaneous compression has a vivid, if unsettling, name: spaghettification. An object, be it a star, a spacecraft, or an astronaut, is drawn out into a long, thin stream of matter, resembling a strand of pasta, before being completely torn asunder. This is not a fate that awaits you at the event horizon itself, however. The severity of the tidal force depends crucially on the size of the black hole. For a smaller, stellar mass black hole, The event horizon is only tens of kilometers across. The curvature of spacetime is so sharp, so extreme, that the difference in gravity over just the height of a human body becomes catastrophic well before you even reach the point of no return. You would be spaghettified outside the horizon, a stark and physical end long before you encountered the deeper mysteries within. But the universe holds a strange kind of mercy in its most monstrous objects. A supermassive black hole, like the one at the heart of our galaxy, has a horizon that is millions of kilometers wide. The curvature at this boundary is far more gentle. The tidal force you would feel with your feet at the horizon, and your head pointing outward might be barely noticeable, perhaps no worse than the feeling of floating in a calm pool. You could cross that threshold intact, sailing into the interior while the paradoxes of frozen time play out for observers far away. Your journey into the darkness would continue, the silence deepening, as you are carried by the current of spacetime toward the final destination. The place where the geometry predicted by our equations truly and completely shatters, the central singularity. This peaceful, quiet descent into the interior is where physics faces its ultimate crisis. The problem is not what happens to the astronaut, but what happens to the information they carry. Every particle in their body, every memory in their mind, every arrangement of atoms that makes them unique, that is information. It is the most precious currency in the universe, the detailed blueprint of what was. And according to the unshakable laws of quantum mechanics, information can never be truly destroyed. It can be scrambled, it can be transformed, but it must always be preserved in some form. This is a foundational principle, akin to saying energy cannot be created or destroyed, only changed. If information were lost, the entire logical framework of quantum physics would collapse, making the past unpredictable and the future incoherent. Yet, here is the contradiction. General relativity, with its smooth geometry of spacetime, paints a very different picture. Once an object crosses the event horizon, it is causally severed from our universe. Its fate is sealed. The equations then tell us that all that matter and energy is inevitably crushed at the central singularity, a point of infinite density where the laws of physics simply stop. From the perspective of the outside cosmos, that information has effectively vanished. It has fallen into a pit from which no signal, no pattern, no echo can ever return. The black hole, in this view, is the ultimate shredder. This creates an impossible standoff. Quantum mechanics insists the information must be preserved forever. General relativity, through the stark reality of the event horizon and the singularity, insists it is erased forever. Both theories are spectacularly successful in their own domains, but they offer mutually exclusive answers for the same event. This is not a minor puzzle. It is a fundamental contradiction at the heart of our understanding of reality. It tells us that where these two great theories meet, at the precipice of the event horizon, our map of the universe contains a glaring, irreconcilable blank spot. The information paradox suggests that either quantum mechanics is wrong, or general relativity is wrong, or more intriguingly, that we are missing a deeper theory that unifies them. The horizon is not just a boundary in space. It is a fault line running through the bedrock of modern physics. The standoff between quantum mechanics and general relativity seemed absolute, a permanent deadlock written into the fabric of the cosmos. Then, in the 1970s, a young physicist named Stephen Hawking performed a calculation that shattered the stalemate and rewrote the rules of the game. He asked a deceptively simple question: what happens when you apply the strange rules of quantum theory not to particles in empty space, but to the empty space itself, right at the edge of an event horizon? The answer was a thunderclap. Black holes, he found, are not black. They glow, they emit radiation, they can, in theory, evaporate and vanish. This glow is now called Hawking radiation, and its discovery was the first concrete sign that the event horizon is not a clean geometric boundary, but a seething quantum frontier. To understand this, we have to venture into the bizarre world of the quantum vacuum. Empty space, according to quantum field theory, is not truly empty. It is a restless, bubbling sea of potential. At the tiniest scales, pairs of particles and their antimatter counterparts constantly flicker into existence. We call these virtual pairs. They borrow energy from the universe for an impossibly brief moment, then annihilate each other, paying the energy back before anyone can notice. This is a quantum fluctuation, a temporary loan against the cosmic ledger that happens everywhere all the time. Normally, this cosmic accounting balances perfectly. The particles appear and vanish in perfect harmony, leaving no trace. But place this quantum froth near the gravitational cliff of an event horizon, and the perfect balance is broken. Imagine one of these virtual pairs popping into existence right at the precipice. In the frantic instant before they must annihilate, one particle finds itself on the wrong side of the line. It falls through the event horizon while its partner is left stranded outside. With its partner gone, the stranded particle can no longer repay the energy loan through annihilation. It is no longer virtual, it becomes real. It gains permanent existence, and with a flicker of energy, it flies away from the black hole into the wider universe. Where did the energy to create this real particle come from? The ledger must still balance. The energy is effectively stolen from the black hole itself. The particle that fell inward carries negative energy into the black hole, reducing its total mass by a minuscule amount. From the outside, it looks as if the black hole has emitted a particle, glowing with a faint, cold thermal radiation. This is Hawking radiation. It is not fire or light bursting from the horizon, but a slow, quantum mechanical leak. The black hole is not pulling particles out of itself. It is quantum tunneling, a ghostly process where particles seem to teleport from just inside the horizon to just outside, because at such scales, the very idea of a sharp, one-way boundary becomes fuzzy. This changes everything. It means the event horizon is not a perfect, static membrane. It is a dynamic surface, trembling with quantum activity. A black hole is no longer a permanent tomb for information, but a slowly evaporating object. Given enough time, a black hole could, in theory, radiate away all of its mass and simply disappear. But this elegant solution creates a new and even more terrifying version of our old paradox. If the black hole evaporates completely, what happens to all the information that fell inside? The Hawking radiation he calculated was purely thermal, like the glow from a hot stove. It contains no details, no fingerprints, no blueprint of what fell in. It is random noise. So when the black hole is gone, has the information been destroyed after all, violating quantum law? Or is it somehow encoded, impossibly scrambled into that featureless radiation? Hawking's glow did not solve the paradox, it deepened it into a crisis, forcing physicists to question whether the horizon itself is even real. Hawking's elegant glow, therefore, created a monstrous dilemma. If information is truly lost forever in the evaporating black hole, then quantum mechanics, our most precisely tested theory of reality, is fundamentally wrong. Most physicists find this unthinkable. The alternative is to accept that the information somehow escapes, encoded within the Hawking radiation. But this escape route comes at a staggering cost. To preserve the sanctity of quantum information, the gentle horizon predicted by Einstein might have to be sacrificed. In recent years, this line of thinking has led to one of the most radical and disturbing proposals in theoretical physics, the Firewall paradox. The argument goes like this. If the Hawking radiation carries away information about what fell into the black hole, then it must be entangled with the interior. Entanglement is that strange quantum link where particles share a single fate. Their properties connected across any distance, but here is the catch. The newly created Hawking radiation particle outside the horizon is also entangled with its long-lost partner, the one that fell in long ago. Quantum mechanics has a strict rule. It forbids a kind of promiscuous entanglement. A particle cannot be fully, faithfully entangled with two different systems at the same time. This is called the monogamy of entanglement. To allow the outgoing radiation to carry new information about the interior, its old entanglement with the infalling partner must be severed. And in quantum theory, severing entanglement is not a quiet process. It releases a catastrophic amount of energy. The calculations suggest this violent quantum divorce would manifest not as a gentle glow, but as a wall of unimaginably high-energy particles waiting at the event horizon itself. An astronaut approaching the black hole would not experience a smooth, silent crossing. Instead, they would be met by a searing barrier of radiation, a literal firewall that would incinerate any infalling object long before it reached the point of no return. This presents physics with a brutal trilemma, a choice between three seemingly sacred principles where you can only keep two. You can preserve the quantum information by having it encoded in the radiation, and you can keep Einstein's principle of a smooth horizon, but then you violate quantum mechanics by having a particle entangled with two partners. You can keep a smooth horizon and obey quantum entanglement rules, but then you must accept that information is permanently destroyed. Or you can preserve information and obey quantum rules, but you must burn Einstein's smooth geometry, replacing the horizon with a deadly firewall. There is no comfortable option. The firewall paradox forces us to question the very nature of the event horizon. Is it the serene geometric boundary of general relativity, or is it a place of violent quantum upheaval, a breakdown so severe it manifests as a wall of fire? The answer, whichever it may be, means that at the precipice of a black hole, space does not just bend. It breaks in a way we are only beginning to comprehend. Faced with a paradox that threatened to unravel physics, theorists began searching for a way to save information without summoning a firewall. Their answer emerged not from discarding our theories, but from pushing them to a breathtaking extreme. It is called the Holographic Principle, and it proposes that the event horizon is not a boundary where information is lost, but a canvas where it is permanently recorded. The key lies in reimagining the very nature of dimensionality. We perceive our world in 3 dimensions of space, but what if all the information needed to describe everything happening within a volume of space, like the entire interior of a black hole, could be perfectly encoded on its 2-dimensional boundary, the event horizon? This is not a metaphor, but a serious mathematical proposal. Think of an ordinary security hologram on a credit card. It is a flat, 2-dimensional sticker. Yet when light shines on it, it projects a full, 3-dimensional image that you can look around. All the information for that 3-dimensional illusion is contained entirely on the 2-dimensional surface. The holographic principle suggests the universe might work in a similar, though far more profound, way. The events we perceive unfolding in the 3-dimensional volume inside the black hole, including the fate of the astronaut, might be entirely equivalent to information being processed and rewritten on the 2-dimensional surface of the horizon. The astronaut falling in is not lost in a 3-dimensional pit, but translated, like a living image, onto a vast spherical film. This would resolve the information paradox with elegant symmetry. From the outside perspective, the information is never lost. It is smeared and preserved on the horizon's surface, exactly as the frozen image we described earlier. From the inside perspective, the astronaut's experience of a 3-dimensional journey continues, because that is simply how the information on the boundary is perceived from within the encoded reality. Both stories can be true because they are 2 descriptions of the same data. This idea transforms the event horizon from a simple one-way gate into the most complex hard drive in the cosmos, a surface where the quantum bits, or qubits, that make up our reality are stored. If this principle holds true for black holes, some physicists argue it might be a fundamental property of the universe itself. The 3-dimensional space we move through, and even the flow of time, might not be primary ingredients of reality. They could be emergent phenomena, illusions that arise from the complex processing of information on a distant, 2-dimensional surface we can never see. At the most fundamental level, the universe might be a hologram. This means that spacetime itself, the stage for all of physics, is not the bedrock. It is a derivative structure that emerges from something deeper and more abstract, a cosmic code written on the boundaries of perception. At the event horizon, where gravity is strongest, this emergent property breaks down, revealing the informational substrate beneath. We are left with a universe that is not made of stuff in space, but of relationships and information, with the event horizon serving as the ultimate screen where the projection of reality begins to flicker and reveal its true, flat nature. But the horizon is only the gateway. The true heart of the mystery, the place where spacetime does not merely bend but is utterly destroyed, lies deeper within. This is the singularity. While the event horizon is a mathematical illusion, a breakdown in our description, the singularity is predicted to be a real, physical endpoint. According to the unflinching equations of general relativity, all the matter and energy that crosses the horizon is funneled inexorably inward, crushed into an infinitely small point at the very center. Here, the curvature of spacetime does not just become extreme, it becomes infinite. The fabric of reality develops a true, sharp edge that cannot be smoothed out by any change of perspective or mathematical trick. Density, temperature, pressure, all the quantities we use to describe the universe, soar to values that are literally beyond definition. At the singularity, the equations of general relativity themselves return a result of infinity, which in physics is not a number, it is a scream. It is the theory's own way of saying, I do not know, I cannot go on. This is where our map of the cosmos turns into a blank page with a warning written in the corner, here be dragons. The coordinate singularity at the horizon was a problem with our rulers and clocks. The physical singularity at the center is a problem with reality itself. It represents a boundary not just in space, but in the very applicability of the laws of nature. Time, as a meaningful concept, is predicted to end here. For anything caught in the gravitational flow, the journey does not merely stop. The idea of a future beyond that point ceases to exist. It is the ultimate breakdown of cause and effect, the final destination where physics, as we know it, simply gives up and walks away. This leaves us staring into an abyss of ignorance, forced to admit that our most powerful theory of gravity is brilliant, beautiful, and ultimately incomplete. It can tell us with certainty that the singularity must exist, but it is utterly silent on what, if anything, lies on the other side. Faced with this terrifying mathematical scream at the singularity, a profound question arises. If the laws of physics truly break down there, could that breakdown ever leak out into the universe we inhabit? Could the infinite, lawless chaos of a singularity ever be exposed, visible to the cosmos? In the late 1960s, the physicist Roger Penrose proposed a startling answer, one that feels less like a law of physics and more like a cosmic safety protocol. He called it the cosmic censorship hypothesis. In its simplest form, it states that nature abhors a naked singularity. Any singularity that forms from the realistic gravitational collapse of a star or other matter must, by the laws of physics, be permanently hidden from view behind an event horizon. The unpredictable madness at the center must be veiled, forever sealed inside a black hole's boundary. Think of it this way. The singularity is like the core of a nuclear reactor, a place of unimaginably intense and dangerous activity. The event horizon is the containment vessel, the thick, impenetrable shield that prevents that raw, chaotic energy from flooding out and rendering the entire facility, the entire universe, uninhabitable. Penrose's conjecture suggests this is not an accident of how black holes form. It is a necessary feature of a stable, predictable cosmos. If you could stand in space and look directly upon a naked singularity, what would you see? The equations suggest pure unpredictability. The smooth geometry of spacetime would be torn apart, and the usual chain of cause and effect would shatter. An object's future could become completely disconnected from its past, making any form of rational physics or even coherent observation impossible. It would be a window into a realm where time runs backward, where gravity becomes repulsive, where the very concepts of before and after lose all meaning. Cosmic censorship argues that the universe simply does not allow such windows to exist. The event horizon is not just a feature of black holes. It is the universe's ultimate firewall, not of energy, but of unpredictability. It protects the orderly, causal world we live in from the anarchic breakdown at its heart. This idea is deeply appealing. It rescues physics from an embarrassing paradox. Our theories predict these zones of infinite breakdown, but then a proposed principle of nature steps in to say, "Do not worry. You will never have to deal with the consequences." The chaos is always contained. It allows scientists to study black holes from the outside, using the predictable laws of general relativity, without having to confront the screaming infinities at their centers. But is cosmic censorship a fundamental law woven into the fabric of reality, or is it merely a hopeful assumption, a piece of theoretical duct tape we have placed over the cracks in our understanding? The hypothesis has never been proven. It remains one of the most important unsolved conjectures in all of theoretical physics. Some sophisticated computer simulations of collapsing stars and colliding black holes suggest that under almost all realistic conditions, an event horizon does form first, cloaking the nascent singularity before it can be exposed. Yet, other highly speculative mathematical models hint at possible loopholes, ways a naked singularity might, in theory, be created, perhaps through the collision of two black holes under just the right conditions. If such an object existed, even for an instant, it would not be a black hole. It would be something far stranger and more dangerous to our understanding, a tear in the causal fabric of spacetime itself, visible to all. The ongoing search for proof of cosmic censorship is really a search to understand the universe's tolerance for its own flaws. Are the infinities in our equations genuine features of reality, or merely signs that our theories are incomplete? Does nature possess a built-in mechanism to hide its own unfinished business, or are we simply hoping it does because the alternative is too unsettling to contemplate? The event horizon stands as the proposed gatekeeper, and its integrity is what separates a knowable, if bizarre, cosmos from one of ultimate and profound chaos. But what if the black hole is not still but spinning? The universe's most destructive objects are rarely static. Most stars rotate, and when they collapse, that spin is conserved, amplified to a dizzying degree. The result is not the simple, silent Schwarzschild black hole we have been discussing, but a whirling vortex of spacetime, a cosmic maelstrom described by a different mathematical key, the Kerr solution. This solution, discovered by New Zealand physicist Roy Kerr in 1963, unveiled a far richer and more bizarre landscape. Here, the event horizon is not a perfect sphere, but an oblate spheroid, bulging at its equator due to the immense rotational forces. And outside this horizon lies something even stranger, a region where the fabric of reality is not just curved, but set into motion, dragged around in a relentless, inescapable whirlpool. This region is called the Ergosphere. To enter the Ergosphere is to step onto a carousel that is spinning at nearly the speed of light. The phenomenon causing this is known as frame dragging. According to general relativity, a massive rotating object does not simply sit in spacetime. It twists the fabric around itself, like a spinning spoon in a jar of honey. Everything nearby, even light itself, is forced to move in the direction of the rotation. Inside the Ergosphere, this dragging becomes so powerful that it is impossible to stand still. No matter how powerful your rockets, you cannot remain stationary relative to the distant stars. You are compelled to move, to orbit the black hole in the same direction it spins. It is a place where the very notion of being at rest loses all meaning, because spacetime itself is flowing like a river. This leads to one of the most astonishing predictions in all of theoretical physics: the possibility of mining a black hole for energy. The process, proposed by Roger Penrose, is a feat of celestial engineering that exploits the twisted geometry of the Ergosphere. Imagine a spacecraft ventures into this turbulent region. From the outside, it carries a certain amount of energy. Once inside the ergosphere, the pilot performs a carefully calculated maneuver, splitting an object into two parts. One piece is sent on a trajectory that plunges into the black hole, following the irresistible flow of dragged spacetime. The other piece is fired backward, against the rotation, with such precise timing and momentum that it escapes the ergosphere entirely. Here is the magic. The piece that falls into the black hole can be given a negative energy orbit, relative to an observer far away. This means that when it crosses the event horizon, it actually reduces the black hole's total mass and rotational energy. To conserve overall energy, the piece that escapes must therefore emerge with more energy than the original whole object possessed. The spacecraft has effectively stolen rotational energy from the black hole itself. This is the Penrose Process, a theoretical proof that the chaotic structure around a rotating black hole is not just a barrier, but a potential power source. It demonstrates that the breakdown of a simple, static spacetime is far more complex and dynamic than a spherical horizon. The ergosphere is a tangible manifestation of spacetime in motion, a region where the universe's geometry becomes an engine, and where the very act of falling can, under the right conditions, release a net gain of energy back into the cosmos. Yet even the ergosphere is merely the outer turbulence of a far stranger interior. The true architecture of a rotating black hole, as revealed by the Kerr solution, is not a simple pit with a singularity at the bottom. It is a layered labyrinth, a set of nested horizons guarding progressively more alien realms. Just inside the outer event horizon we have discussed, the point where escape becomes impossible for any object, lies another boundary. This is the inner event horizon. For a falling astronaut, crossing this second horizon would be another silent, uneventful transition, but its implications are profound. It is often described as a gateway from a universe of crushing gravitational forces into one where those forces might, in a sense, reverse. Some theoretical models suggest that beyond the inner horizon, the radial pull of gravity could become repulsive, potentially offering not a point of infinite crushing, but a passageway. This leads us to the most enigmatic chamber in this cosmic labyrinth, the Cauchy horizon. Named for the French mathematician Augustin-Louis Cauchy, this is not a barrier against escape, but a barrier against prediction. It is a boundary where the universe's ability to determine the future completely breaks down. To understand why, we must revisit a core assumption of all physics: determinism. In our normal world, if you know the exact state of a system at a given moment, the laws of physics allow you to calculate, at least in principle, its future state. The past dictates the future. The Cauchy horizon is where this principle dies. Within this region, the equations of general relativity no longer provide unique solutions. The future becomes mathematically undefined. It is as if you have sailed your ship by perfect charts your entire journey, but upon crossing a specific longitude, the map turns blank, and the ocean currents no longer obey any predictable pattern. Your past voyage no longer constrains where you can go next. Anything could lie ahead. This represents a deeper, more fundamental pathology in spacetime than the singularity itself. A singularity is a place where quantities become infinite and our equations fail. The Cauchy horizon is a place where the equations still work, but they stop giving answers. They offer not a single future, but an infinite number of possible futures, with no law to choose between them. Here, the chain of cause and effect does not just stretch or bend, it severs. An object's trajectory is no longer dictated by the forces that acted upon it in the past. In this realm, the very concept of because may lose all meaning. Could you encounter your own past self? Could effects precede their causes? The mathematics suggests that within the Cauchy horizon, such paradoxes are not just possible, they are unavoidable. This is not merely a breakdown of physics, but a breakdown of narrative, of story, of the logical sequence that allows us to make sense of reality itself. It is a whisper from the equations that the orderly, causal cosmos we cherish might be a local phenomenon, a stable bubble in a wider reality where such order is the exception, not the rule. And this leads to a disturbing, almost philosophical question. If you crossed this ultimate threshold, would you be traveling into a new universe, or simply into a realm where the idea of a universe no longer applies? This mathematical mirror of a black hole is known as a white hole. If a black hole is a region of spacetime from which nothing can escape, a white hole is its perfect theoretical opposite, a region of spacetime that nothing can enter. It is a cosmic fountain, eternally spewing out matter and energy while rejecting any attempt to approach its boundary. You could fly toward it at any speed, but you would find it impossible to cross its horizon, forever repelled by the geometry of space itself. The concept emerges directly from the equations of general relativity, which are symmetric with respect to time. Run the film of a black hole's formation and evolution in reverse, and you get a white hole. Instead of a star collapsing forever inward, you would see matter and radiation exploding outward from a singular beginning, a bang instead of a crunch. This time reversal symmetry suggests that if black holes can exist, then white holes should be mathematically possible solutions as well. They are the universe's hypothetical ejector seats, places where existence is forcefully expelled into the cosmos. The most tantalizing idea, however, is that these two opposites might not be separate objects at all, but two ends of a single, impossible tunnel. This tunnel is an Einstein-Rosen bridge, more popularly known as a wormhole. In this speculative picture, the black hole's event horizon and the white hole's event horizon could be connected by a throat of spacetime, a shortcut through the cosmos. An object falling into the black hole could, in theory, be ejected from the white hole somewhere else, or even in another time. It paints a picture of the universe as a piece of cosmic Swiss cheese, threaded with hidden passages. Yet for all its mathematical elegance, the white hole remains a ghost in the equations. Physicists widely consider them to be physically improbable, if not impossible, in our actual universe. The reason cuts to the heart of cosmic history. While the laws of physics might be time-symmetric, the universe itself is not. It has a clear arrow of time, defined by increasing disorder or entropy, from a highly ordered beginning in the Big Bang. Real gravitational collapse, like a star falling in on itself, is a messy, irreversible process that drives entropy upward. Its time reverse, a white hole emerging from a singularity and spitting out ordered structure, would be a process of decreasing entropy, like a shattered glass reassembling itself and leaping back onto a table. Such an event would violate the overwhelming statistical trend of the cosmos. White holes, therefore, serve a profound purpose not as real destinations, but as theoretical beacons. They illuminate the fundamental asymmetry of time in our universe by showing us what is mathematically allowed, but physically forbidden. They highlight that the cosmos we live in is one where gravitational collapse happens, where horizons are one-way doors inward, not outward. Their probable impossibility reinforces the unique, irreversible direction in which reality unfolds, from a singular beginning toward an uncertain future, where black holes are the sinks, not the sources of existence. So if black holes and white holes are two sides of the same mathematical coin, could they be physically linked? This speculative bridge is known as a wormhole, a shortcut through the broken and folded fabric of spacetime. The concept is deceptively simple. Imagine the universe is the surface of a vast sheet of paper. Two distant points are far apart if you travel across the sheet. But if you could bend the paper, bringing those 2 points together and then punching a tunnel directly through the higher dimension between them, you create a shortcut. That tunnel is the wormhole. In the language of general relativity, the extreme curvature at a black hole's event horizon might not lead to a dead-end singularity, but could instead flare out into a tunnel or throat that connects to another region of spacetime. In this picture, the horizon you cross isn't the end of your journey, it's the entrance to a cosmic subway. The other end of that tunnel could, theoretically, be the event horizon of a white hole, explosively ejecting you somewhere else in our universe, or even in a different universe altogether. It's a breathtaking idea, offering a solution to the tyranny of cosmic distance, turning a black hole from a tomb into a gateway. The mathematics of Einstein's equations do not forbid such structures. They appear as valid, if exotic, solutions. But moving from a mathematical possibility to a physical reality introduces monumental, likely insurmountable, problems. The first and most critical is stability. The wormholes described by the simplest equations are dynamic. They are not static tunnels you could stroll through. The moment they form, the throat would pinch off violently, snapping shut faster than the speed of light. Anything attempting to pass through would be crushed or severed by the collapsing geometry. To be a traversable shortcut, the tunnel must be held open against this relentless gravitational urge to close. And that requires something truly bizarre, a substance known as exotic matter. This isn't just rare or unknown matter. It's matter that defies the normal energy conditions of our universe. Exotic matter would need to possess negative energy density, creating a kind of gravitational repulsion to prop the throat open. While tiny amounts of negative energy density might be possible through quantum effects, like the Casimir effect, the quantities needed to stabilize a human-sized wormhole are astronomically beyond anything we know how to create or even conceive of. It's like needing a material that weighs less than nothing to build an arch that holds up the sky. The second problem is one of paradox. If traversable wormholes exist, they could easily be used to build time machines, creating causal loops where you could travel back and interact with your own past. This introduces the same universe-breaking paradoxes we encountered at the Cauchy horizon, where the logical sequence of cause and effect unravels. Most physicists view this as a powerful argument that nature must prevent such structures from forming in the first place. So while wormholes captivate our imagination, illustrating how the breakdown of normal spacetime might enable fantastic possibilities, they remain almost certainly in the realm of the non-physical. They are a brilliant stress test for our theories, showing us the boundaries of what geometry alone can allow, and where the deeper laws of quantum gravity must step in to say no. The mathematics paints a picture of profound breakdown, but the universe offers its own evidence. For decades, event horizons existed only in the pages of theoretical physics, a ghost in the equations. The challenge was monumental. How do you observe an object defined by its ability to trap light? Astronomers became cosmic detectives, learning to see the unseeable by watching how the darkness interacts with the light around it. One of the earliest and most compelling clues came from watching stars dance around nothing. At the very heart of our Milky Way galaxy, telescopes tracked the orbits of several stars over many years. Their paths were not random but followed precise, looping ellipses like comets orbiting a hidden sun. By applying Newton's laws, which still work perfectly well at a distance, astronomers could calculate the mass of the invisible object tugging on them. The result was staggering: an object with over 4 million times the mass of our Sun, crammed into a region of space smaller than our solar system. The density required was so extreme that no known object, not a cluster of stars, not a cloud of dark matter, could explain it. The only thing that fit the data was a supermassive black hole, its immense gravity herding the stars, with the event horizon marking the boundary of its invisible presence. Another powerful line of evidence comes from watching matter in its final moments before the plunge. In systems called X-ray binaries, a normal star is locked in a tight orbit with a compact, incredibly dense object, often a neutron star or a black hole. The intense gravity of the dense object strips gas from its companion star. This gas does not fall straight in, but spirals inward, forming a swirling, superheated disk known as an accretion disk. As the gas particles rub against each other in this cosmic whirlpool, they heat to millions of degrees, emitting powerful X-rays. Here, the nature of the central object becomes clear through a critical absence. If the dense object is a neutron star, it has a hard, solid surface made of ultra-dense nuclear matter. When the infalling gas finally hits that surface, it releases a final, tremendous burst of energy, a distinctive spike in the X-ray signal. But for many of these systems, astronomers see no such spike. The X-ray emission simply rises to a peak and then drops off sharply, as if the gas and the energy it carries is vanishing into a silent abyss. This is the observational signature of an event horizon. The gas crosses that final boundary, and without a surface to crash into, its energy is swallowed whole, leaving no final flash for our telescopes to catch. It is the sound of a door closing without a slam, the key evidence that we are not looking at the hardest surface in the universe, but at the edge of nothingness itself. The theoretical ghost finally took a physical form in April 2019. For the first time in human history, we looked directly into the abyss and saw its silhouette. The Event Horizon Telescope collaboration did not just take a picture. They performed an act of cosmic cartography on an unimaginable scale. This was not a single telescope, but a planet-sized virtual instrument created by linking observatories across the globe, from the high deserts of Chile to the volcanic peaks of Hawaii, all synchronized by atomic clocks. Their target was the supermassive black hole at the heart of the galaxy Messier 87, a gravitational titan over 6.5 billion times the mass of our Sun. The resulting image, a fiery orange ring encircling a central darkness, is one of the most profound scientific portraits ever captured. But what we are seeing is not the event horizon itself. We are seeing its shadow cast upon the fabric of the universe. The bright ring is the accretion disk, the superheated whirlpool of gas and dust spiraling inward at nearly light speed. The central darkness is the shadow of the black hole, a region roughly 2.5 times larger than the event horizon. This shadow is created because the black hole's gravity is so intense it bends the paths of light rays from the accretion disk behind it. Some of that light is captured completely, vanishing across the horizon. Some is bent so severely it orbits the black hole multiple times before escaping to our telescopes. This creates a bright, thin ring of light just outside the shadow's edge, known as the photon ring. It is the signature of spacetime warped to its absolute limit, a place where gravity is so strong that light itself is forced to travel in circles, tracing closed orbits around the point of no return. That dark central shadow, then, is the closest we can come to a direct image of the event horizon. It is the absence that proves the presence, the silhouette of a bottomless pit etched in light. This image was not a static snapshot. It was a precise measurement of spacetime geometry. The size and shape of the shadow matched the predictions of general relativity for a spinning black hole with stunning accuracy. We were not just looking at a dark spot. We were witnessing the raw, twisted geometry of Einstein's universe, confirming that at the edge of a black hole, space does not merely curve, it ties itself into light-trapping knots. The shadow is the map, and it shows the territory is every bit as strange as the equations promised. The shadow in the image was a silent, static monument. But black holes are not always solitary giants. Sometimes they dance. In the deepest reaches of space, two such objects can find themselves locked in a mutual orbit, a final, fatal embrace that ends not with a flash of light, but with a shudder in the fabric of reality itself. This shudder is a gravitational wave. For a century after Einstein predicted their existence, these ripples in spacetime were a theoretical ghost. Then, in September 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, felt the universe tremble. The signal was a cosmic chirp, a rising frequency and amplitude that told a precise story. It was the sound of two black holes, each roughly 30 times the mass of our Sun, spiraling toward one another at half the speed of light in a galaxy over 1 billion light-years away. In the final fraction of a second, their two event horizons merged into one. The resulting tremor in spacetime, a passing stretch and squeeze smaller than the width of a proton, had traveled across the cosmos to whisper its story to us. This was not an observation of light or X-rays or any electromagnetic signal at all. It was a direct measurement of moving geometry. we were listening to spacetime itself ring like a bell. The beauty of this signal lies in its clean, mathematical story. The gravitational wave chirp is divided into 3 clear phases, each a chapter in the merger. First, the inspiral. As the 2 black holes orbit, they lose energy by radiating gravitational waves, causing their orbits to tighten and their speed to increase. The waveform we detect mirrors this, a rising tone and crescendo that is a perfect fingerprint of their masses and orbits. Then comes the merger, the moment the 2 distinct event horizons touch and become one highly distorted horizon. This produces the peak of the signal, the loudest part of the chirp. Finally, the ringdown. The new, single black hole is not a perfect sphere. It is misshapen, vibrating like a struck gong as it settles into a stable, smooth form. The gravitational waves it emits during this settling phase are a dying series of waves, like the fading tone of that gong. This ringdown is a direct probe of the new event horizon's properties. By analyzing these fading ripples, physicists can measure the final black hole's mass and, crucially, its spin. The entire sequence, from inspiral to ringdown, is a pristine test of general relativity in the most extreme environment imaginable. The strong field regime just outside the merging horizons where gravity is billions of times stronger than in our solar system. Every merger detected since that first one, by LIGO and its European counterpart Virgo, has been a resounding confirmation. The observed signals match the predictions of Einstein's equations with astonishing fidelity. This means the objects we are detecting are not just massive, not just dark. Their behavior perfectly aligns with what we expect from pure spacetime geometry, from event horizons with no solid surface to complicate the collision. When 2 neutron stars merge, the signal is different, often followed by a brilliant kilonova explosion of light and heavy elements. But when 2 black holes merge, the signal is clean, sharp, and ends in silence. All the furious energy of the collision, equivalent to several suns converted pure energy, is carried away by the gravitational waves, and any remaining disturbance is swallowed by the new, larger event horizon. This silent finale is itself a signature of the horizon's reality. The dynamic, violent process of 2 points of no return becoming one leaves no electromagnetic debris behind, only a tremor in the cosmic fabric. Gravitational wave astronomy has given us a new sense, allowing us to hear the universe. And what we are hearing in those chirps from the dark is the sound of horizons dancing, merging, and proving that even in their most violent moments, they obey the profound and beautiful geometry written over a century ago. The silent mergers confirmed by gravitational waves are a triumph for Einstein's geometry, but they do not resolve the paradoxes screaming from within the mathematics. The conflict between a smooth horizon and the laws of quantum information remains. To escape this deadlock, some physicists propose a radical solution. Perhaps the event horizon, as classically described, does not actually exist. These are not fringe ideas, but serious attempts to replace the mathematical breakdown with a new, stable state of matter. A final fortress that prevents the formation of a true point of no return. One such proposal is the Gravastar. Imagine a black hole's immense gravity not creating an empty pit, but triggering a phase transition in the fabric of spacetime itself. Like water freezing into ice, the space inside a certain radius could transform into a bizarre state of exotic vacuum energy, a kind of dark energy that exerts a powerful outward pressure. This inner core would be surrounded by an ultra-thin, ultra-dense shell of ordinary matter, frozen just at the point where the event horizon would have formed. From a distance, a gravastar would look and behave almost exactly like a black hole, trapping light and bending spacetime fiercely. But there is a critical difference: no sharp horizon and no singularity. Matter falling in would strike this incredibly dense shell, where information could, in principle, be preserved or even reflected back, avoiding the paradox of eternal loss. It is a cosmic egg, with a brittle shell protecting a mysterious interior, replacing the infinite cliff with a tangible, if exotic, surface. Another idea emerges from the depths of string theory, called the fuzzball. This proposal abandons the idea of empty spacetime inside a black hole entirely. Instead, the entire region within what we call the Schwarzschild radius is packed with a gigantic, tangled knot of fundamental strings, the vibrating threads of reality proposed by the theory. This fuzzball has no smooth horizon, no vacuum interior. Its surface is a complex, fuzzy boundary where the strings extend out like a dense thicket. There is no clear point of no return because the fuzzball is all return, a massive, coherent object with a defined, albeit incredibly complex, structure. Information about what fell in is not lost behind a horizon, but is encoded in the specific vibrational patterns of this cosmic knot, preserved forever in its topology. Then there is the concept of a black star, an object so compact that light is severely redshifted and trapped in near-perpetual orbits, but from which some radiation eventually, over cosmic timescales, still manages to leak out. It would appear black for all practical purposes, but mathematically, it never quite forms that perfect one-way membrane. These alternatives share a common philosophical goal: to protect the universe from its own mathematical extremes. They seek to replace the terrifying infinities and causal breakdowns with something physical, however strange. They are attempts to build a cosmic dam before the river of spacetime plunges over a waterfall into nothingness. The dam itself might be made of materials we can scarcely conceive of, but it represents a universe that refuses to have true edges, a cosmos that finds a way to keep information in play, no matter the cost. Whether any of these ideas are correct is unknown. They are difficult, if not impossible, to test with current observations, as their external appearance mimics a black hole so closely. Yet their existence is profoundly important. They illustrate that the event horizon is not a settled fact, but a hypothesis. It is the simplest solution from one magnificent theory, general relativity. But when that theory clashes with another magnificent theory, quantum mechanics, the very ground it stands on may need to be re-examined. The search for these alternatives is not an attempt to dodge the weirdness of black holes, but to embrace an even deeper weirdness, one where spacetime itself might have states of matter, and where the darkest objects in the sky are not holes, but something else entirely. The paradoxes we have uncovered are not mere puzzles. They are signposts pointing toward a new physics. Resolving the contradictions between the smooth horizon of general relativity and the information-preserving demands of quantum mechanics is now widely seen as the single most promising path to a complete theory of quantum gravity. This is the holy grail of modern physics, a framework that would describe the cosmos at its most fundamental level, from the vast expanse of galaxies down to the quantum foam of spacetime itself. The event horizon is the ultimate laboratory for this quest, a place where both theories are pushed to their absolute limits, and their incompatibility becomes impossible to ignore. To cross this frontier, scientists are constructing radically new visions of reality. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating loops of energy. In this view, the entropy of a black hole, and thus the information it contains, might be accounted for by the specific vibrational states of these strings at the horizon. Loop quantum gravity takes a different path, suggesting that spacetime itself is not smooth and continuous, but woven from a network of discrete, finite loops, a kind of cosmic fabric with a finite weave. This granular structure could prevent the formation of a true singularity and modify the nature of the horizon, turning it into a transitional zone rather than a sharp boundary. And then there is the holographic principle we explored earlier, formalized in the AD/CFT correspondence, which mathematically demonstrates that a gravitational theory in a volume of space can be perfectly equivalent to a quantum field theory living on its boundary. This provides a concrete, if profoundly strange, mechanism for how the three-dimensional information of a black hole's interior could be encoded on its two-dimensional event horizon, offering a potential escape from the information paradox. Each of these approaches, in its own way, is trying to describe the microstructure of the horizon, to answer what spacetime is made of at the scale where it breaks. They are not just tweaking Einstein's equations, they are attempting to rewrite the foundational language of the cosmos. The struggle to understand the event horizon is therefore forcing a revolution far greater than simply explaining black holes. It is compelling us to reconsider the very nature of space, time, and information. We are being led to a startling possibility that spacetime itself is not a fundamental stage, but an emergent phenomenon, a collective illusion that arises from deeper, more abstract quantum processes. The horizon is the crack where this illusion begins to falter, revealing the machinery beneath. To peer into that darkness is to glimpse the next chapter in our understanding of everything. This journey through the darkness has shown us that the event horizon is far more than a distant oddity. It is the universe's most extreme laboratory, a place where our deepest theories are stress-tested to the point of shattering. We have witnessed the breakdown of simultaneity, where the very idea of a shared now dissolves. We have grappled with the information paradox, a standoff between quantum law and gravitational geometry that threatens the logical bedrock of reality. And we have confronted the singularity, a mathematical scream where physics as we know it simply walks off the job. Each of these failures is not a dead end, but a brilliant signpost. They are the cosmos telling us in no uncertain terms that our current maps are incomplete. The profound contradictions at the edge of a black hole are not flaws to be hidden, but clues to be followed. They are the very guideposts that will lead us to the next great synthesis, a theory of quantum gravity that weaves space, time, and information into a seamless whole. So the next time you see an image from the Event Horizon Telescope, or read about a new chirp from the gravitational-wave observatories, remember you are not just looking at data. You are witnessing humanity peer into the cracks of reality itself, gathering the pieces we need to build a deeper, truer story of everything. Stay curious, for the horizon is just the beginning.